Hello. Well, you may remember that I started about a fortnight ago a long-term test of solar panels with a solar panel stuck up on the roof of my bungalow and the data coming back down to the PC here, which is always on. And I come in from time to time and I can turn around in my study and see what it's up to. And I thought I'd just update you on the data we've got so far. Obviously, we need much more than a fortnight's data to have anything sensible, but it's just interesting to see how it's going. Well, it's a lovely sunny day today and an almost clear blue sky. And the sun is over there. So the panel is in full sun and spring has sprung in my garden. And there are lots of bees feeding on the nectar on this shrub of mine, which smells sweet. So there's 846 milliwatts, and this is the graph from this morning. Blue line is power and the red line is the optimum voltage, which is pretty erratic as the sun comes up from sunrise, but then settles down at about 5.6 volts. So that was the first day. And we got, you can see top left, 3 watt-hours during the 24-hour period. I'm afraid it clouded over in the afternoon, so we didn't get a continuation of the nice morning. What a difference a day makes. It's 10 AM on day 2, and it's a miserable, cloudy day with a light drizzle. And we have 117 milliwatts, whereas yesterday we had about 700 milliwatts. It's essentially nothing at the moment. So that day ended with total generation of 1.3 watt-hours, which was the worst day of the first week. Overall, the first week we averaged a generation of 3.1 watt-hours per day, with the best day being 5.2 watt-hours and the worst being 1.3. So quite a large variation day to day. The next week began with 3 glorious days of sunshine, with the newspapers being full of stories of it being the warmest February day since records began. And on this first day we generated 5.7 watt-hours. On the second day we generated another 5.7, and on the third day we generated 5.8 watt-hours. So that was really good. But you would have noticed that there seems to be a hole in the middle of these, all 3 of those recordings, somewhat between 11 and 1 PM. Well, it's 11:40 AM, and as you can see, my very carefully placed solar panel is in shade. The reason for this is these bloody trees here. The sun is up there. I don't think there's anything I can do about this. It happens for a couple of hours in the middle of the day. We'll just have to cope for it on the output. It'll get worse when the trees get in leaf in the spring, but on the other hand the sun will be higher in the sky, so I think we may escape. Later in the afternoon, it's nearly 2:30 now, the sun seems to have got up far enough so it's above the tree. Well, it's a miserable, wet, overcast day, and we have virtually nothing. 0.1 watt-hours, and it's just coming up to noon. Virtually nothing. This the blue line is the power, the one at the bottom there. Well, the second week was much better than the first, with an average generation of 4.6 watt hours. 3 really good days, or maybe 4 really good days, and 1 bad one. That miserable wet day that I just filmed came outside the fortnight, but it generated only 0.6 watt hours, which is less than half of the previous worst day. So the worst day so far has generated less than a tenth of the power that was generated on the best day. But for the purposes of discussion now, I'm just going to assume that on average we can generate 3 watt hours per day. Woodstock is now measuring the current consumption of its electronics 5 times a second. This histogram here is produced from the last test we did at Weston down on Southampton Water, and it gives an average current consumption of 188 milliamps. And a maximum of 900 milliamps and a minimum of 30. We measured the power consumption as 0.94 watts, which is equivalent to 22.6 watt hours per day. It seems that one panel is generating about 3 watt hours per day, so we need at least 8 panels. That is assuming no shading of the panels, which of course is not true. That's based on measurements taken in February. We can work out what we might get in the summer by looking at the solar elevation. So it may be that in June we would get double that power. So maybe we only need 5 panels if we only worked in this summer. Our friend Ollie Epsom of YouTube channel Drawing Board 82 sent me some interesting data that he obtained from a sort of 10 kilowatt solar panel on the roof of a house that he used to own. And the blue line here shows the kilowatt hours produced per day, and the red line is a fit of a sinusoidal curve that can be used to predict how much power the panel would generate at any particular month of the year. You can see that up here at the peak in June it generates 5.5 kilowatt hours, and at its worst situation in December it's only 0.3, which is a factor of 18 down. If we go to February, it's about where we are now, it's about 2.25. So that also kind of confirms the calculation I just did based solely on solar elevation, because 2.25 is times 2 is about 5.5. Well, not quite, but there are other factors apart from just the solar elevation that change the generation as a function of the time of the year. I was just trying to work out how many of these solar panels could fit conveniently on Woodstock at the moment without coming over the sides of the hull. It's quite windy out there at the moment, so I've got to use paperweights to hold these things down. So, and this one, obviously this one actually goes here, but I can't put it there because of this cable thing. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And can we? No, we can't really have one there. No. So that's 13 quite easily, which is more than 8, which is all we need, assuming there's no shading. However, if we look at the deck camera from the Dragon camera of the last test at Western, you can see that there's quite a considerable scope for shadows from the sails obscuring one panel after another. Never more than half, I would say, but very unpredictable shading. We should exclude the shading from that electronics box, which would be below decks in a real situation. But it's the shading from the sails that we need to be concerned about, and the mast, of course. Somehow we have to form an estimate of how much shading is going to occur. Well, that's a taste of the data that we're getting from the solar panel long-term test. Obviously we can't draw any conclusions from just a fortnight, but I wanted to just show the kind of way that we might analyse the data. There are all kinds of variations that we've got to take into account. So far we've had a 10-to-1 variation in the power generated from day to day within a week. According to Ollie's graph, there is an 18-to-1 variation between them, June and December. It's 10 o'clock. So there's an 18-to-1 variation in generation from June to December. We've got the shading of the panels by the sails and the rigging. We've got the fact that we may not always be loading the panels at the optimal amount. And we've also got the fact that we've got to charge a battery, and charging batteries is not 100% efficient. And we've also got to use electronics to upconvert the solar panel voltage to a suitable voltage to charge the batteries. And that electronics is unlikely to be more efficient than 95%. So all in all, there are lots of factors to take into account. And we'll be doing that over the coming months, hopefully. Thanks very much for watching.